Welcome to Python tutorial 2 of the course Time Dependent Quantum Chemistry. In the earlier Python tutorial, we have learned different small programming with Python. We have used arithmetic computation, and we have shown a few loops and how to plot a graph. Now in this tutorial, we will go over how to represent a wave function, and later we will find out how to represent an operator. But here we will show how to represent a wave function in Python programming and how to get the norm, which we need to normalize the wave function, and also we will calculate the expectation value. So let's go over this tutorial. The wave function and the operator, these are the two key constituents of quantum mechanics. The wave function represents the state of the system, which is represented by psi x. The state of a system is represented by the wave function. On the other hand, when operator acts on the wave function, we get the observable. So when this operator acting on the wave function, we get the observable. Observable which can be observed experimentally. Therefore, because these are the two constituents of quantum mechanics, the first step towards obtaining numerical solution of any quantum mechanical problem is to represent the wave function and the operator in appropriate computer programming data structure. That's the first step we should have if we want to use numerical solution of quantum mechanical problem. We have to convert this wave function and the operator in the computer programming data structure. Computer programming data structure. So this question is how to represent them. Almost all currently available numerical methods for solving quantum mechanical problems make use of grid representation of the wave function and the operator. So one way to do this is the grid representation. What is grid representation? I will present it. A wave function by its nature is continuous. So what would be the procedure to transform this operator into computer programming structure? This is something which we will look at later, not now, not in this tutorial. We will just stay focused on the wave function part. So operator will be dealing with operator later. But we know that wave function by its nature is continuous. That's the way we have made the postulate of quantum mechanics. It is a continuous function, continuous in the coordinate space. So whatever variable we use, here we are using x as a variable, which is the position space. So it's going to be continuous in the position space. And this property of an wave function comes from the postulate of quantum mechanics. So it's continuous in position space. But in the grid representation, the representation which we'll use to represent a wave function in the computer programming data structure, that is the grid representation. In the grid representation, what we will do, a continuous wave function is a continuous wave function. So grid representation is following. a continuous wave function is expressed on a set of position grid points. So what does it mean? The entire position space, this is the x-axis, entire position space, theoretically x-axis goes from minus infinity to plus infinity, but in computer programming data structure we will not be able to use this infinite limit. So what we will do, we will consider one x minimum and one x maximum value. Within this range we will express the wave function, and we will assume that in this boundary x minimum and x maximum wave function becomes 0. So because it is 0 here already, so it will be 0 at minus infinity and plus infinity as well. So we are following the boundary condition in the computer programming. So the boundary has to be selected such a way, the finite boundary, this is the finite boundary we are selecting in the x-axis, this is the x coordinate. So finite boundary has to be selected such a way that the wave function will become 0 before that boundary. So within this boundary what we will do, we will not be able to represent it a continuous wave function. We have to divide the entire problem domain. This is called problem domain. This x coordinate, it is also position space, it is also called problem domain. Or the position space. This entire position space will be we will be dividing it into an uniform grid. So we will have a discrete value of x, and corresponding to discrete value of x we will have discrete value of the wave function. And each one, let us say this is x naught, this is x1, this is x2, this is x3, x4, x5, like this way, and then this is, if I have n number of such grid points, then I have, this is xn minus 1, because it's starting from x0, that is why it is going up to xn minus 1, that is the maximum value of x we get. So what we do here, this under grid representation we actually discretize the continuous wave function. A wave function by its nature, but from the postulate of quantum mechanics, it has to be continuous, but we have to represent in the computer programming, we have to represent a continuous wave function in a discretized wave function. So grid representation gives me a discretized wave function discretized wave function. So discrete values of x I will get. So instead of drawing this, I have to draw it like this way. It was like this, and I have now discrete values of wave function, and this is going to represent the wave function in the Python programming. I get discrete values on the x grid. So to understand this discretization of wave function further, we have to divide the certain range of x coordinate. As I said that this x coordinate, I cannot take minus infinity to plus infinity limit in computer programming. I have to take the finite limit x minimum and x maximum, and this range, so x has to be then x minimum less than equals x maximum. So x value would be in between this x minimum and x maximum value, and we'll make sure that when you are defining this finite domain, we have to make sure that the wave function becomes 0 at the boundaries, as if it already has become 0. So the idea is that at minus infinity and plus infinity it will be 0, and the requirement for wave function to be 0 at 0 value at minus infinity and plus infinity comes from the fact that this wave function should live in the Hilbert space. We have studied this Hilbert space, meaning of Hilbert space in module 4, where we have discussed the square integral. Every wave function has to be square integrable so that we can normalize it. So the entire x axis will be divided by a suitable small step size delta x to produce the uniform discrete grid. So this is the uniform discrete grid we produce. So we have, let's say, n number of discrete values of x within this range. We have n number of discrete values. So one can write down here is that x n minus 1 minus xn equals delta x. That's the separation between each grid points. And xn minus 1, this xn minus 1, this is the final grid point, which is the x maximum, that we can get by taking x naught plus delta x multiplied by n. Then I get this, the maximum value. X naught is the minimum value. This is the x naught is the minimum value. So I will plug that in. So what I get is that xn minus 1 this is going to be n minus 1. It is n minus 1 times I have to add, then I get this x naught, x the final value. So if we rearrange it, I can write down xn minus 1 minus x naught divided by delta x equals n minus 1, or n I get 1 plus xn minus 1 minus x naught divided by delta x. So how many grid points I have, it depends on the spacing I am selecting and the range I am selecting. This is the range we have selected. Xn minus 1, that's the maximum range, and this is the minimum value in the range. So this many number of grid points we have, and because we have this many grid points, we'll have that many values of the function. And this is exactly what we have shown here. A continuous wave function which is represented by dot line here, but we have to represent it on this grid. So on each grid point I get the value of the function. So when a continuous wave function is represented on the x grid, we get these values x naught at x equals x naught value. I get function wave function value y naught, then psi x1 I get y1, psi x2 I get y2, like this way, and then psi xn minus 1 I get yn minus 1. So these are the values we get, and in linear algebra one can represent this entire set of values as a column matrix. So psi x would be represented in the matrix form as y0, y1, y2, y3, yn minus 1. That's the column matrix we form, and that's the representation. And this matrix, this is a column matrix. This column matrix can be represented in the Python programming by an array. So pretty much we have got an idea how we are going to represent the entire wave function in the computer programming. We have to prepare the array. So before we prepare the array, first we have to create the X grid. That's the way we have said that we have to prepare the X grid, where we have to define the certain range, which is, let's say, minimum to maximum. This is the range I have to select, and then after selecting range I have to select also delta x. Then I can create this X grid, and on the X grid we have to find out the wave function values to represent the wave function. We have already realized from Python tutorial, the first Python tutorial, that this A-range functionality we have already used. A-range functionality, start, stop, step of SciPy, this SciPy module we are using. It can actually return a list of evenly spaced discrete values of x within the given range. So this is the range, start, stop, that's the range, and then then this is the difference between each grid point, each points, evenly spaced points, we can get it. So we'll use this A-range functionality to create that, and I'll just remind that in A-range functionality, when you use that, stop, this part will not be used in the sequence or will not be included in the sequence. So A range, if I write 1, then 5, then 1, it will return me evenly spaced discrete values of x in a following way. It will give me 1, then it will give me 2, because the difference I have selected to be 1, then it will give me 3, then it will be 4, then it is supposed to give me 5, but because 5 is stop, and the way this A-range functionality works, it will just exclude the last one. So I get back this as a list of values. To be technically correct, although, we should remember that we have also briefly mentioned that in the previous Python tutorial, that A-range functionality returns an array, not a list. So although we are calling it as a list, but technically this is an array we get. So, and the difference between list and an array in Python programming, the list program, this list is actually Python's built-in program, which is present in Python programming, but arrange functionality, this comes from SciPy. This is actually SciPy's functionality. Now, this list functionality of Python's built-in functionality list cannot be used for linear algebra routines which are implemented in SciPy. For that, we have to use always this array. So that's the reason why we are using arrange functionality. It returns an array. And one-dimensional array is nothing but the column matrix, or it can also be represented as a row matrix as well. So we will use this arrange functionality. In general, the data structure which is used to represent mathematical matrix in computer programming is called array. So this is the definition of array is, it is the mathematical it is the to represent it represents a mathematical matrix in computer programming. And array can be n-dimensional, it can have dimensionality n, but two-dimensional array is called matrix, and a one-dimensional array is called a vector. This is an one-dimensional array which we have prepared for the X grid. Python does not have intrinsic functionality to deal with the array or different array operations, broadly linear algebra routines. For that, one needs to import scientific functionality, specific functionality from SciPy. So that's the reason why we are using SciPy. So you have to import this arrange functionality from SciPy. So we will prepare the grid, and grid preparation is very simple. We will move to laptop now, and we'll prepare the grid. We will first import, and this hash will indicate that anything written after the hash would not be executed in the Python programming. It is just for our information. So we are importing the required libraries. We will name it wave.py, and from SciPy import arrange functionality. Then we'll create the X grid. For that, we have to define X minimum. X minimum we are defining 100. X maximum, remember we are defining 100.1 because this point will be excluded from the list, and dx, that's the difference between grid point, adjacent grid point, is 0.1. That's why we have selected 100.1, so that it is, so the entire range is going to be minus 100 to plus 100. This minimum is minus 100 and maximum is plus 100. Then we will just specify x equals a range x minimum x maximum dx. That's the construct of the arrange functionality. Then we'll just write down n equals len x. What it does, it will try to find out the number of elements. I will move to the presentation in the slide. So this length is a Python's built-in functionality, which is len, x. So what it does, if x is an array, then it will find out number of elements present in the array. That's the functionality of length. This is Python's built-in functionality. One doesn't need to import it from anywhere. We'll move to the laptop, and then I'll just print n. I'll print n to check how many elements I have in the prepared grid, and I will also print x. That's the x grid I have. So if I want to now run the program, I have to use Python. Then we have given wave name .py. .py extension has been given, and we can run the program. When you run the program, we see that we are getting 2001 number of elements. This is the first print n, that's the first printing, and second printing is that the values of the x grid. The values of the x grid is -100, then -99.9, then -99.8. That's the way values should be. So we will move to this slide. We have 2001 number of n, so n equals 2001, and if I am plotting, I'm printing the entire x array here, and entire x means grid points I'm writing, and if I look at the grid points, it is starting from -100 to and ending at +100 with a spacing between adjacent grid points is 0.1. That's exactly what we wanted to do. This is the construct which we have used already. Now we can recheck whenever we are doing some numerical method we are following. If we are following numerical methods, in the beginning we should always try to match the result with an analytical solution. So we have already seen that the n can be calculated. N is nothing but number of elements I will have in the grid point. So I have prepared the grid points from -100 to +100 with a separation 0.1. That's the grid points, x grid I have prepared. So how many elements I have, that is given by n equals 1 plus x maximum minus x minimum divided by delta x, which is nothing but 1 plus x maximum was 100 minus x minimum was -100 divided by delta x equals 0.1, which is nothing but 200 divided by 0.1, which is 2001. So length, this functionality is giving me the correct number of elements I have in the x grid, and to stop to make this range to be -100 to +100, I just remind that x maximum we have taken to be 100.1. Because the last that's the way a range functionality works. A range functionality, the stop part, the stop will not be included in the sequence. That's the way it works. So once we have already discretized the once we have a x grid, on this x grid will now represent or discretize the wave function. So when you are discretizing a wave function, you have to take one example. One can take an example of, let's say, Gaussian function. It's just a wave function. That's the one representation of the wave function, a Gaussian function. And we will take this example to demonstrate that how to discretize the wave function on the x grid. So the first part of this programming is quite understandable now. We have created the X grid first, and then we have to discretize it. When you are discretizing it, it is very simple. When an array is used as variable for a mathematical function such as this psi x. So psi x is an array. If this is an array, then we produce, if we directly write down psi x equals e to the power minus x square, then we produce another array containing function value corresponding to each element of the array variable. So basically, so this construct directly representing this construct, because x is an array, I will produce another array of psi. So if x is an array which is starting from 100 to plus 100, then I will get psi, which can also be expressed as y, is also an array, and this array will have the elements where function values will be presented corresponding to each grid point. That's the way it works quickly. And this plotting part, we are familiar with this plotting part by using this matplot library, pyplot submodule. We are plotting it to make sure that we have the wave function, the desired wave function. So we will move to laptop, and we will now will not delete this part, we'll just keep it as it is, importing the libraries. Now we will add one more line here because we are going to plot it. That's why we are importing plot and show functionality from matplot library pyplot. So from matplot library dot matplotlib dot pyplot import plot and show, both I need. And then I have created this grid. This part is creating the grid, and then I will now discretize the wave function, and this is very simply done. I can name it psi, psi. I could name it y or something else as well. Just I'm naming it psi equals, this is exponential. So exponential is not available. This mathematical function is not available with Python. It has to be imported from SciPy. So I have to import from SciPy. So I have written so psi. So I am importing this exponential from SciPy, and then now this psi will be psi will be defined. Psi is defined as minus x square. Square is double star 2. This is the psi, and next what we would like to do is that we would like to plot so that I can see what I have discretized. So plot the wave function. I can plot it. Plot construct is x comma y. Here x comma, it cannot be y, the name is psi. So x comma psi, and that's the construct is, it will plot and it will take the x array and y array, and corresponding element wise they will plot it, and finally I have to give this show command to display the wave function. So if I now run this program, I get the wave function. One can select a particular x limit to show the Gaussian function for a shorter x limit, because it will give you the correct shape of the Gaussian function. see it in a longer x scale, it may not give you the right representation. It is just a representation problem, but it plots the correct wave function. So we have this discretized wave function plotted already, and this psi, we will move to the slide right now. So this psi has now an array. So both x and psi is an array. So the idea of discretizing the wave function is to prepare the array associated with the wave function on the grid points. So once we have represented a wave function, here we have taken an example of Gaussian wave function, we can go ahead and normalize the discretized wave function. We will continue the session, we'll continue learning how to represent the wave function, how to normalize a wave function, how to normalize a discretized wave function in the next session.